Something I want to talk to you about now is the speed of transmission of the energy from one end to the other. In other words, I want to talk to you about wave velocity. Now, again, in school, you'll have learned that there are three things you need to know about a wave: velocity, frequency, and wavelength. So let's get Kuzhi Liang to demonstrate wave velocity. Now, the wave is going to transmit down a transverse wave. What tells you whether it's going to move quickly or slowly? And the answer is the force that is operating between the particles that are moving. We're going to begin with the dancers not linking arms, so the force between them is quite small. And if you look, you'll see that the wave moves slowly down the line. In other words, the wave velocity is low. So did you notice the wave moved very slowly down the line? We can measure the wave velocity because I'm going to count in seconds from when I say go to when the lady at the end moves. Let's see how long it takes for the wave to go down. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it took about 12 seconds for the wave to go that distance. How far is that distance? Let's measure it in meters. Approximately 1, 2, 3, 4, 5, 6 meters. 6 meters in 12 seconds. What's the velocity of the wave? Velocity equals distance over time, and so the velocity of the wave is 12 meters divided by 6 seconds. In other words, the wave velocity was 2 meters per second. Now, let's increase the force between the particles, between the people. Link arms tightly. So let's try and see how many seconds it takes for this wave to go down. 1, 2, 3, 4. 4 seconds. Before it was 12 seconds. This wave moved 3 times quicker than the earlier wave. So the velocity of a wave is the velocity with which the energy is transmitted from one place to another. 4 seconds to go 6 meters. You can work out the speed of that wave. So now, just let's look one more time at a wave where the energy travels slowly and a wave where the energy travels quickly. The velocity of the wave measured in meters a second. Let's have the fast one first. Everybody link arms. And now a slow wave, a small force between the particles. Unlink your arms. Go. Much slower because there was only a small force between the particles. Now this applies to sound waves. Even though sound waves are longitudinal waves, sound travels at different speeds according to things like the air temperature. If the air is cold, all the air particles are closer together. And so a sound wave travels quicker through cold air than it does through hot air. Similarly, sound travels quicker in Fundsolling than it does in Thimphu, because we're 8,000 feet up here. The air particles are further apart because the air pressure is up here is lower. In Phuntsholling, the air particles are all closer together. So when I go, in Phuntsholling, the sound travels more quickly than if I go, up here in Thimphu. So if we understand about waves and what waves are, it helps us to understand and it helps us to predict what's going to happen if I send a sound wave through water, for example. Now, in water, the water molecules are very close together. Water's much more dense than air. So if I send a sound wave through water, it travels much more quickly than it does through air. So let's try a sound wave, fast and slow. The sound wave up here in Thimphu. These people are air particles. Up here in Thimphu, high altitude, low pressure, the air particles are a little bit separated. Are you ready? Go. Thank you. Now let's go down to Phuntsholling, where the air particles are all closer together. And let's send the same sound from me to you in Phuntsholling. Go. Much quicker. The energy moved much more quickly. So remember, the velocity of a wave depends on all sorts of factors. The velocity of a sound wave depends on air temperature, air pressure. It also depends on the material that the sound is going through. Through water it goes quickly. Through a solid material, the sound travels very quickly. Earthquake waves. They are mainly transverse waves. And the speed with which an earthquake wave goes from the epicenter of the earthquake to other places depends on the sort of rocks that the earthquake wave is being transmitted through. So wave velocity is really important. Now, the next thing you need to know about waves is frequency. So what's the frequency of a wave? The frequency of a wave is how many times a second the particle moves. How many times a second? I'm going to make you go once a second. 1, 2, 1, 2, and then watch it transmit down the line. 1, 2, 1, 2, 1, 2. Frequency. How many times in 1 second does he carry out a complete vibration? Just notice this. A complete vibration means watch, out, back, and back to the beginning again. I'm going to do that. A complete vibration. Out, back, and back to the middle again. Now watch. This is now going to be a high frequency. Are you ready? High frequency. And low frequency. You're wearing a red Tego. You're wearing a blue Tego. Why does yours look red and yours look blue? And the answer is, your Tego and your Tego reflect different frequencies of light. Red light is low frequency. So the light coming off your Tego is low frequency waves. The light coming off yours, blue is high frequency. So the light coming off your Tego is high frequency light waves. And green in between Green is medium frequency light waves. Microwaves, if by chance you've seen a microwave oven, they are even lower frequency than the red Tego. But ultraviolet light and X-rays are much higher frequency than the blue light coming off from here. So the frequency of light waves tells us what color we're going to see. Frequency is very important, and in sound waves too. With the sound wave, a low frequency is a deep sound. High frequency is a high sound. If I ask my friends to sing do, re, mi, fa, sol, la, ti, do, as they go up, the frequency of the sound wave gets higher and higher. In other words, the air particles are vibrating quicker and quicker. Can you do do, re, mi, fa, sol, la, ti, do for me? 1, 2, 3.
Do, re, mi, fa, sol, la, ti, do.
Absolutely. So there we have low frequency sound waves, high frequency sound waves. So for light, the frequency tells us the color. For sound, the frequency tells us the pitch. So we've now got velocity of the wave, how quickly the energy transmits. Frequency of the wave, very important for sound and light and everything else. Now we have wavelength. Now that's a bit more difficult to demonstrate. I'll see if my friends can demonstrate wavelength to us. The wave's going like that. He's standing in the middle. Follow the wave pattern, and it gets back to where he was over there. Look where he is on the stones. Look where he is on the stones. Here, the people were not in the middle. They were out and then in. And if we look there, the distance between this chappie and that chappie is one wavelength. Look at the wave. That's one wavelength. Now the wavelength is very, very important. And it's the distance between two particles, him and him, which are at the same point of movement. Here and there, these two people were at the same stage of movement. These people in between, some were out, some were in, he's at the same stage. He is about to move forwards, he is about to move forwards. The distance between the two, and you can see it on the ground, is one wavelength. If we have a high frequency wave, if these were moving backwards and forwards faster, the wavelength automatically becomes shorter. So now they were moving backwards and forwards at a high frequency, and I said stop, and this is how they looked when I said stop. You notice the wavelength from there to there is shorter. Notice though, the wavelength is the distance from him, from his feet to his feet. It's not the distance measured like that, it's the straight line distance between his feet and his feet. Short wavelength, high frequency. And you could think of it like a seesaw. High frequency, short wavelength. Low frequency, long, big wavelength. Wavelength and frequency are like the two arms of a seesaw. When one gets bigger, the other gets smaller. When one gets smaller, the other gets bigger. High frequency, short wavelength, low frequency, long wavelength. And this is true of all waves. And next, we'll look at the relationship between velocity, frequency, and wavelength, a little formula which says velocity equals frequency multiplied by wavelength. We've just seen a wave made by people moving backwards and forwards. We've talked about the difference between a transverse and a longitudinal wave. So now let's just put it all together a little bit and then talk about the wave formula. Now, what I've tried to draw here is a transverse wave. It's not a very good drawing. I'm sure the drawing in your textbook will be much better than mine. But at least it serves to show some basic things. First of all, this thing, the wavelength. Now, in your textbook, I think the abbreviation for wavelength is a rather funny thing which looks like that, which is the Greek letter lambda. It's the Greek letter L, and that stands for wavelength. Now, when we were looking at the people, the wave moving down through the people, we saw that if I suddenly stopped them, in other words, took a photograph of them and looked at them from above, you'd see the people laid out in a pattern like this, a wave pattern. And I said that the difference, or the distance, I should say, between two people who are about to do the same thing is called one wavelength. So this is one wavelength. And you measure wavelength in centimeters or meters. I also mentioned another quantity called frequency. And I said that frequency was how often this person vibrated backwards and forwards in 1 second. A high frequency, the person is going backwards and forwards quickly. A low frequency, they're going backwards and forwards slowly. And the abbreviation for frequency is F. And whereas wavelength will be measured in meters, frequency is measured in a unit called Hertz. Unit is named after a very famous German physicist of 150 odd years ago who actually did a lot of research work on waves. So his name has been commemorated in the unit of frequency, which is called a Hertz. And sometimes if you look on sound apparatus, recording apparatus, you will see something might say 50 mH little z. That means 50 megahertz. Mega means a million. So 50 mH means 50 megahertz. And this means that the vibrations are happening 50 million times a second. Think of that, 50 million times a second. If I'd asked a dancer of the Kujilayang to vibrate backwards and forwards 50 million times a second, it would actually be quite difficult for them. If we think of sound, a sound wave may typically, a sound like la, is about 1,000 hertz. In other words, 1,000 vibrations a second. So if I had a loudspeaker here, and I could see the loudspeaker cone, and it was emitting a noise like la, something like that, and if I were to touch the loudspeaker cone, I can feel it going in and out, and it's going in and out 1,000 times a second. And that's what's creating the vibrations of the air particles. So frequency is very important. Measured in hertz, 50 megahertz means 50 million vibrations a second. And the other quantity that I showed you with the dancers was the speed with which the energy goes down the wave speed, how long it took from when I went like this to the person at this end to how long it took to reach the person at the other end. That's the wave velocity. The wave speed, the wave velocity. And the symbol for that is v, and it's measured just like other velocities in meters per second. So that's relatively straightforward. Now, there is a formula which links together the wavelength of a wave, the frequency of a wave, and the velocity of a wave. Formula tells us, and you will have learned this at school, the formula tells us that v is equal to f multiplied by lambda. Velocity equals frequency times wavelength. That is known as the wave formula. So, for example, I know that a sound wave up here probably travels at about 700 meters a second. If I take a noise like that is about 1,000 hertz. So I can calculate what the wavelength is. The wavelength of a sound wave, if it sounds like is approximately, well, v equals f lambda, so lambda equals v over f, it will be approximately 700 over 1,000. Cross off the noughts, it's about 7 over 10, which is 0.7 meters. So the wavelength of a sound like is about 0.7 meters. We can do the same calculation for light. It's a bit more complicated. You know the velocity of light is 3 times 10 to the 8 meters a second. If I take a light wave of, say, 100 mega or 1,000 megahertz, I can calculate the wavelength of the light will be 3 times 10 to the 8 all over 1,000 times 10 to the 6, and you can carry out that calculation yourself. The wavelength of light is very, 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 very small. I also said today that frequency and wavelength are like the two sides of a seesaw. High frequency, low wavelength. Low frequency, long wavelength. High frequency, low or short wavelength. Low frequency, long wavelength. So it's just like a seesaw. And this shows us that it's like a seesaw. Now, I just want to say something. And this will probably annoy many of you, and it may annoy some of you teachers as well. For 10 years, I have been trying to persuade everybody in schools to read this as velocity equals frequency multiplied by wavelength. If I turn it into numbers, 6 equals 3 multiplied by 2. Now, so many of you learn to say 6 equals 3 into 2. That is totally and absolutely wrong, because into is short for divided into. So if I say into here, I really should put a a divided sign, which of course is not correct. So please, could I ask you all, whenever you see a multiplied sign there, don't say 3 into 2, say 3 multiplied by 2. 3 times 6 equals 18. 3 multiplied by 6 equals 18. 3 into 6 equals 2. Now, just let me go back to the wave formula. Velocity equals frequency multiplied by wavelength. There are 3 quantities there, and you may in school have been taught a nice little triangle which helps you remember. Frequency multiplied by wavelength equals velocity. Velocity is frequency times wavelength. If I want to find the frequency, what's the formula for the frequency? All you have to do is cover F with your hand, and what are you left with? Velocity over wavelength. If I want to find the wavelength, just cover wavelength with your hand, and what are you left with? Velocity over frequency. This little triangle, to help you work out which formula you need, applies whenever you get 3 quantities and one equals 1 times the other. So V equals IR in electricity. Exactly the same thing works. To find F, cover it, you're left with V over lambda. To find lambda, cover it, you're left with V over F. And if you want to find V, cover it, and you're left with frequency times wavelength. It's a quick little way of remembering things. So, the wave formula, velocity equals frequency times wavelength, very easy to use. You simply insert the figures and out comes the answer. Now there's just one last quantity about waves to show you on my very bad picture of a wave, and that is when the dancers were moving backwards and forwards, how far did they move? Sometimes they might move just a little bit, other times they may move a long way. If we think of a dancer just here, for example, the dancer there will move from here to there. Similarly, this dancer will move from here to there. This dancer will move from here, that's meant to be the same height, will move from there to there. This distance, which you see is half the total movement of the dancer, that's called the amplitude of the wave. And that's a very important quantity too, because for a sound wave, the amplitude of the wave tells you how loud it is. So if you've got something playing music very, very quietly, the amplitude of the wave is small. But if you've got a great big hi-fi set blasting out music in a disco, the amplitude of movement of the air particles is very big. So the amplitude for a sound wave tells you how loud or how soft. The amplitude of a light wave will tell you how bright the light is. A light wave with a big amplitude will create bright things to see. A dim light, a low amplitude. So waves are everywhere. We depend on waves for sight. We depend on waves for sound. We depend on waves to transmit television signals that you're watching with the use of now. We depend on waves, radio waves, for our mobile phones. Earthquakes happen and create waves. In the sea, you have waves. Do you know, if you saw pictures of the Japanese tsunami, those great waves coming over the land, the safest place to be in the middle of a tsunami is actually on a boat in the middle of the ocean. Because these great waves come, they lift up the boat, and then the boat goes down, and then they lift the boat again. So the boat just goes slowly up and down. But when the waves get to the land, they're stopped by the land, and that's why they come over and flood everywhere. So remember, if ever, God forbid, you're in a tsunami, best thing is set out to sea in a little boat. And in the Japanese tsunami and in the tsunami that happened around Thailand and Indonesia, the people who were okay were the fishermen from the villages who were out on the sea in their fishing boats, going up and down, and the poor people who were there on the land got swamped by these great waves. Waves are everywhere. Waves are one of the most important things in physics. And in the next program, I'll go on to talk a little bit more about sound waves and light waves. And remember, please, if as a result of any of these programs you have any questions, if I say anything which you haven't quite understood or you want to ask more questions about, please get in touch with BBS. Because what we want to do is we want to make a program one day soon which is just about your questions. So please don't be shy. I was asked the other day an excellent question arising from the radioactivity program, where I said that electrons get shot out of the nucleus. But in the nucleus, all you've got are protons and neutrons. And this school student said to me, so if all you've got in the nucleus are protons and neutrons, where do the electrons come from? Not from the ones going around. They come from within the nucleus. So where do the electrons come from? Now that was a really intelligent question, and I was able to answer it. So if you have questions from anything I say, get in touch with BBS. And finally, let's just see me. I'm probably a bit better at physics than I am at dancing. So let's just have 1 minute of our Taché Lebe to close this program on what are waves.